And let's go to start doing this problem. It say find the curl is denoted like this, of the vector field F. The curl of a vector field is a new vector field. And what it say this new vector field, the curl. The curl, it say the tendency of the vector field to rotate. So it's a local property, it depends on the points. So when we are going to find the curl of the vector field, we are going to find the curl of a vector field at each point. And how we find the tendency to rotate of the vector field? The tendency to rotate is done, and I will explain why is this like this, is done by calculating the partial derivative of x, the partial derivative of y, the partial derivative with respect to z, and the components are x, y, z, x, y, z, x, y, z. So what is the tendency to rotate? Well, the curl of f will be a new vector field. So we can write like this, the curl of f, a vector field. And it will be I, the derivative with respect to the y of x, y, z, minus the derivative with respect to the z of x, y, z, minus j, the derivative with respect to the x of x, y, z, minus the derivative with respect to the z of x, y, z, plus k, the derivative with respect to the x of x, y, z, minus the derivative with respect to the y of x, y, z. And this will be the curl of f, the tendency to rotate at any point. It will be y, it will be a vector, and it will be the derivative with respect to the y is xc, minus the derivative with respect to the z is xy, minus j, the derivative with respect to the x, yz, the derivative with respect to the z of xyz, the derivative with respect to the z of xyz is xy, plus k, the derivative with respect to the x is yc, minus the derivative with respect to the y is xc. So this is not zero at any point except at the point 0, 0, 0. So there is a tendency to rotate of the vector field. And the measurement of the rotation of this tendency is store the information on this vector, on the curl of f. The magnitude, for example, the curl of f at the point 1, 1, 1 will be I 1 minus 1 minus j 1 by 1 minus 1 by 1 plus k 1 by 1 1 by 1. So it's 0. So there is no tendency of the vector field to rotate at the point 1, 1. And what is the tendency to rotate at the point 2, 1, 1? It will be 2 multiplied by 1 minus 2 multiplied by 1 minus j 1 by 1 minus 2 multiplied by 1 plus k 1 by 1 minus 2 by 1. So this is not 0, so there is a tendency to rotate. And in which direction is the tendency to rotate? Y2 minus 2 is 0, so 0y minus 2 minus 1j minus 1j, 1 minus 2, 1 minus 2, and k will be 1 minus 2 is minus 1, minus 1k. So the tendency to rotate at the point 2, 1, 1, at the point 1, 1, 1, there is no tendency to rotate. But at the point 2, x equal to y equal 1, and z equal 1, at this point, the vector, the curl of f, is minus 1j minus 1k. Minus 1j will go like this. Minus 1k will go like this. So the vector will go like this, the curl. This will be the curl of f at the point 2, 1, 1. So there is a tendency to rotate in this direction. And what is the magnitude of the tendency to rotate? The magnitude of the curl of f at this point is a square root of 1 squared plus 1 squared. So it's a square root of 2. This is what we are going to practice. Well, the only detail is that here there is a plus sign. This is plus sign because this is minus, with this minus is plus. Okay, let's go to practice more problems. Now let's go to do a similar problem. So we know the definition of the curl of f. So we know how to find the curl of f. Do it has any mystery? No. Let's imagine that we can do this partial derivative. So this is the x component, e to the x sine of y, minus e to the x cosine of y, and the zeta component is 0. So cosine of y, cosine of y. So what is the curl of f? The curl of f for the y components will be 0. For the j components will be 0, will involve this, minus this that doesn't depend on z will be 0. So the only component that will survive is the k component. And the k component will be the partial derivative with respect to the x of minus e to the x cosine of y minus the partial derivative with respect to the y of e to the x sine of y. And what is that? This is the k components will be the partial derivative of e to the x is e to the x cosine of y minus the partial derivative of with respect to the y is e to the x by the partial derivative with respect to the y of sine of y, which is cosine of y. So it will be equal k minus 2 times. So it will be minus 2 times e to the x cosine of y k. That means that there is a tendency to rotate of this vector field that is measured at every point with this expression. So for example, at the point at the point x, y, z equal, let's say, 1, pi divided by 2, and 3, zeta equal 3, first of all, we notice that the curve, the tendency to rotate of this vector field, it doesn't depend on z, because indeed the vector field doesn't depend on z. So at this point, the curl of f, the tendency to rotate is minus 2 times e to the y cosine of pi divided by 2, but cosine of pi divided by 2 is 0, so the tendency to rotate is 0. It means that the curl of f is 0. There is no tendency to rotate. So what it means, the tendency to rotate? How we measure this tendency? Well, we measure this tendency by finding the curl of f, by finding this operation. But how it comes this operation into the game? Well, the curl of f, imagine that there is a curl of f somewhere. Let's say like this. This is the curl of f. So there is a vector field f, and you find the curl of f. Let's say this is the curl of f at this point. What it means, the curl of f? It means that if you imagine that you put here a small area, DDS, this small area will have a normal vector, n. And let's say that this normal vector is a unitary normal vector. So let's say that is the vector n with a hat. Let's say that you see the projection of the curl of f. The projection of the curl of f onto the normal is the curl of f dot dn. And this will have a length. And the projection of the curl of f will be the curl of f components in the direction of the n, of the vector n. And what is the magnitude of this curl of f? The curl of f will be the projection, so it will be this. And this is the curl of f in the direction, is the magnitude of the curl of f in the direction of the normal vector. And what exactly is this thing? It means like this. It means if you imagine this curve C of I that englobes the area, and you imagine that you take the vector field f and you do the line integral over the curve C of the vector field f scalar ddr over the vector C, the curl of f, this is equal to the line integral of the vector field f ddr per unit of area. So when you take the limit, when the area goes to 0, of the magnitude of the line integral per unit of area, when the area goes to 0, this is the curl of f in the direction n. This is the magnitude of the curl of f in the direction n. So the idea of rotation are related with circulations, with line integral. So is the line integral. So now there is a small detail. The line integral is performed in a way that if you walk through the line, through the curve, your left-hand side must go to the inside of the curve. So this is the direction in which you perform the line integral. Because if you perform in the contrary, in the opposite direction, you will have a negative amount of line integral that if you perform in the other direction. So this is C, and this is the line integral. So, as a conclusion, the components of the curl of f in the x direction is the line integral over the curve C of f scalar ddr per unit of area, that is perpendicular to the direction x. So if this is the x direction, and this is the curve of F. The projection of the curve of F will be this, and this is the curve of F in the x direction. And the curve of F is in the x direction is related with the line integral of the vector field F through the curve C when the area ddy ddz goes to 0. So this is a density function. The curve F marks the line integral per unit of area. Line integral per unit of area when the area goes to 0. Or when the area approaches to 0. So this is the concept. So what is the curve of F in the y direction? Well, you will have the curve of F in some direction. What is the magnitude of the curve of F? How you will calculate? You will see the projection on the y direction, and you will find this vector, the curve of F. This is equal to the line integral. So you will do the line integral over the curve C, this curve C, of the vector field F scalar ddr per unit of area. But the unit of area here, we imagine a square, will be ddx by ddc. So this is the idea. The idea is to relate the curve of F with the tendency to rotate of the vector field, and to relate the tendency to rotate of the vector field with line integrals. Problem. It's verify that the curl of this vector field at the point 1, 0 is pointing in the direction J. Is f of 1, 0 is the vector 0i plus 1j. At the point 0, 1 is pointing in the direction minus I. So it would be like this. And if I find the vector field F at the point minus 1, 0, I will find that the vector field goes like this. And if I find the vector field F at the point 0, minus 1, the vector field will go like this. So there is a tendency to rotate. It's clear that there is a tendency to rotate of the vector field. What is the amount of the tendency to rotate? The curve of F. The curve of F is a new vector field that it say at each point here, what is the tendency to rotate? And the tendency to rotate, it will obtain doing this calculation. I, j, k, partial derivative respect to the x, partial derivative respect to the c, minus y plus x, 0. And the curve of F, the only component that will survive will be the k component. And the k components, the amount of rotation that is on the k components is the partial derivative respect to the x, 1, minus the partial derivative respect to the y of minus y. This is minus 1. So the curve of F will be 2 times k. But 2 what? What's the unit of these 2? Well, let's say that F is an electrical field. If F is an electrical field and we are talking about the curve of E is newtons, is force per unit of charge. Is force per unit of charge. So what is the curve of F? What is the unit? 2 watt. 2 watt. So is the line integral per unit of area. The area is in meters per square. And the line integral is E, newtons per coulombs, line integral per meters. So is E scalar DDL or DDR. So it's Newton per coulomb per meters. So this means that the two have units. And the unit of the two, in the case that F is an electrical field, will be newtons per coulomb, newtons per coulombs per meter. And these are the units of these two. So this problem say that the curve of F is 2 wherever you are, because it doesn't depend on where you are. It doesn't depend on X or Y. What happens if I do this integral? The integral over a curve C of F scalar DDR of this vector field. So I do this integral. The line integral of F. And what is F? F is the vector field minus yi plus xj ddx. DDR is ddxi plus ddyj. So the line integral that I want to find over a curve C is the line integral of minus y ddx plus x ddy. So let's go to this line integral. So we have the vector field. We know how the vector field is doing. The vector field is doing like this, like this. It's always tangent to a circle. It's always tangent to the circle. So let's go to use polar coordinates to do this integral. So in polar coordinates, y, this is r. The y's are cosine of theta. The x is r cosine of theta. The ddy is r cosine of theta dd theta. And ddx is r sine of theta dd theta with a minus sign. Minus r sine of theta dd theta. So the integral over the curve C, and the curve C is a closed curve of radius r, will be the integral of minus y minus r sine of theta by ddx. Minus will be plus the r squared and sine squared dd theta plus the integral of x ddy. The x will be r cosine of theta, and the ddy will be r cosine of theta, cosine square of theta, dd theta. And this will be on a closed curve that I will go around one time, so it will be between theta equals 0 and theta equal 2 pi. And this will be r squared multiplied by the integral between 0 and 2 pi of sine squared plus cosine squared of theta, which is 1 by dd theta. So this will be 2 pi, the integral from 0 to 2 pi, it will be 2 pi. 2 pi r squared is this integral. And what is the line integral of f scalar ddr per unit of area? Is The line integral is 2 pi r squared. Divide by pi r squared, wow, is 2. So the idea of the curl is that it's the line integral per unit of area. Now, if we go and we see at any point, and we did the line integral of the vector field by this trajectory, this path, this line integral. What if we do like this? We take any point, and we do the line integral around the circle, around the point of radius r, and we take the radius r to goes to 0 in a way that is the line integral per unit of area when the area is equal to 0. It goes approach to 0. Can we do it? So at any point, if the vector field is the same one, is minus yi plus xj. So I want to do the line integral here on this point xy. So on this point, this is the vector field that exists at the point xy. So this is the point xy. And there is a vector field here. Now I want to do the integral of f scalar ddr. But ddr is the integral of f scalar ddr. ddr is ddxi plus ddyj. So it will happen the same expression. Is the integral of x f that is y minus yi dd minus yi plus. Now we have different vector fields. It's a vector field in 3 dimensions, and it says determine if the vector field is conservative. One of the things of a vector field to be conservative means that f can be expressed like minus, well, in mathematics, no need the minus, f is the gradient of some function f. So some function little f, the gradient of f will produce a vector field. And the vector field will be this one. So what happened with the curl of f? Well, the curl of f will be I, j, k, partial derivative respect to the x, partial derivative respect to the y, partial derivative respect to the z, and the gradient of f, the partial derivative of f respect to the x, the partial derivative of f respect to the y, and the partial derivative of f respect to the z. So is the curl, this is the curl of f, but f is the gradient of f. Okay, and what will be this? Well, if you do it, you will see that it will appear here the partial derivative of y respect to the z, and here it will appear the partial derivative of z respect to the y. It will cancel. Conclusion, if f equal to the gradient of f, so it exists a function, a potential function whose gradient is the vector field, then the curl of f is 0. So determine if the vector field is conservative. Well, if the vector field is conservative, the curl of f is 0. Also, it works in both these directions, the theorem. Only you need to be careful to have a function that is well defined, continuous, A nice function. So let's go to the problem. The problem says determine if the vector field is conservative. Well, what we will do, we determine if the curl is zero. If the curl is zero, the vector field is conservative. So let's go to do it. Y, J, K, so the curl of F will be a new vector field. Is y, j, partial derivative with respect to the x, partial derivative with respect to the y, partial derivative with respect to the c, and sine of c, sine of x, and sine of y. So if this is zero, the vector field is zero. So let's go to find one component, the I component. The I component will involve the partial derivative with respect to the y of sine of y, cosine of y, and the partial derivative with respect to the c of sine of x, and this is zero. So this vector field is not conservative. I was waiting to be conservative, so it's not conservative because at least one component is not zero. Let me check if I did the correct calculation. Sine of c, sine of x, sine of y, partial, the I component will be partial derivative of respect to the y of sine of y, which is cosine of y, and partial derivative with respect to the c of sine of x is zero. Sine of x doesn't depend on c, so the partial derivative. So the curl of f is not zero. It's not zero because at least the I component is not zero. With the j component, I can calculate the k components of the curve, but no need. We know that it's not conservative. What it means is that it's not conservative. It means that it doesn't exist a f whose gradient is the vector field. You cannot find a function f whose gradient is the vector field. Wow. Let's go to the next problem. Now the following problem says find a potential function for the conservative vector field. So it says that it's conservative, the curl of this vector field should be zero. So we can check that the curl of this vector field is zero, but let's go to trust that they are not cheating us, that the curl of f is zero. So because it says that it's a conservative vector field, so if it's a conservative vector field, it exists a potential function f, whose gradient of f is the vector field f. The problem is asking who is the potential function. Well, the gradient of f is a vector field whose derivative, who has the component, the derivative of f with respect to the x, derivative of f with respect to the y, and derivative of f with respect to the c. Okay. And I want this to be the vector field. So I want this to be x, y squared, c squared I, plus x squared, y, c squared j, plus x squared, y squared c, k. X squared, y squared, c, k. And this will allow me to put three equations. The partial derivative of f with respect to the x equal x, y squared, c squared. The second equation will be that the partial derivative of f with respect to the y should be x squared, y, c squared. And the third equation would be that the partial derivative of f with respect to the c should be x squared, y squared, c. X squared, y squared, c. And I wonder who is f? who is the function f whose partial derivative with respect to the x is x y squared cx squared. Well, if I choose x squared y squared 1/2 zeta squared, when I do the partial derivative of f respect to the x, I will have x y squared c squared. But if I choose also the same one plus a function phi1 that depend on y and z, also the partial derivative of f respect to the x, because this would be 0, would be this expression. Now, let's go to the second challenge. What is f if the partial derivative of f respect to the y should be x squared y c squared? Well, it's clear that if I choose like f, x squared y squared c squared will work, because the partial derivative of f respect to the y will be 2 times, the 2 will cancel, x squared y c squared, and I will obtain this. So for the moment, I have that this is a potential expression for the potential function. Also, if I add another function that depends on x and z, it will not change anything, because the partial derivative of f respect to the y of this expression will be 0. And what would be f here? Well, the partial derivative of f with respect to the z should be x squared y squared z. So if I choose f to be x squared y squared zeta squared, when I make the derivative, I will obtain this expression. And same again, if I choose phi sub 3 of x comma y, arbitrary phi 3, also the part. So at the end, what is the function that I will choose as the potential function? So I have here the same expression. So I will use common factors and non-common factors. What are the common factors? The common factors for the f of x, y, z, the potential is 1/2 x squared, y squared, and c squared. Plus the non-common factor, there is no common factor. So I will add a c, and it will work. So this is the potential. Let's go to the next problem. Find the divergence. Oh, this is a different subject. The divergence of a vector field is not a vector field. It's not a vector field. It's a number, or it's a scalar function. It assigns a number to every point x comma y. And what is this number? The number is obtained by this. First of all, let's go to work with the expression. The gradient of f is like the dot product of two imaginary vectors. So the first vector is the vector derivative respect to the xi plus j derivative respect to the y. That is the nabla vector dot the f. The f is fxi plus fyj. So y scalar y is 1 and y scalar j is 0. So it would be the partial derivative of f sub x respect to the x plus the partial derivative of f sub y respect to the y, and this is a number. At the point 1, 2, this is a number. So let's go to find the divergence. Oh, and what it means, the divergence of a vector field. The divergence of a vector field means find the divergence of a vector field at a point x comma y the divergence of a vector field is a number, and this number is related with something. You take the point where you want to find the divergence. You imagine a sphere. Well, in this case, is the plane. You imagine a circle. And you find the flux of the vector field crossing the surface. So you imagine that you calculate over this sphere or this disk, we can say, F scalar dDA. And you make the limit when the volumes goes to zero of the flux per unit of volume. And you expect this limit to be a number. And this number is the divergence. So to know the divergence of a field, you simply you find the flux of the vector through the sphere to the object that you put its center at the point, and you find the flux per unit of volume when the volume is increased to zero, it goes approach to zero. And you expect that this number, as you go to zero, this number will approach to some number because there is a limit. You expect this to happen. So the expression for the divergence is this one. And now it takes the work to find, let's say that we find a volume, we choose a small volume, ddx, ddy, ddc. We have a vector field here, let's say F, and we want to find the divergence. So how we will find the divergence? So we need to find the flux. So the flux through, let's go to find the flux through this side and the flux through the other side. So we find the flux to all the side of the the flux of the vector field. The flux that is crossing, entering means negative flux, going out means positive flux, entering means positive, negative, because the normal vector is n, and the vector field, it will go like this. So F scalar n will be dds, will be, in this case here, will be negative, but in the other side, the F will go in this direction. The normal always goes outside of the volume, so the F scalar dds will be positive. So I will have that the flux entering through this side is negative, the flux going out of this side is positive, and the next flux is the sum. So let's go to do it. So f of x, the combo, you see that to find the area, to find the flux over this surface, we need to find f of x by ddy by ddc. But And to find the flux through this area, we need to find the force that exists, the vector field that exists, also for d dy ddc. So this calculation is made at the point x equal, let's say, x0. So we call this point the point x0. So this is the x-axis, sorry, x0 plus the ddx, plus ddx divided by 2. And this is made at the point x equal x0 minus ddx divided by 2. So what is f of x? F of x evaluated at the point x0 plus ddx divided by 2, comma y, comma z, is the same f of x that exists at the point x0, the component x of the field, a comma y0, comma theta 0, plus the change in f of x when I move in the direction of x. So I'll go to this side of the plus the partial derivative respect to the x by ddx, but ddx I have chosen to be ddx divided by 2. Same thing for f of x at the point x0 minus ddx divided by 2, comma y, comma z. It will be the value of the component at the point x0, comma z, comma y0, comma zeta 0, minus the change in the component of the vector field multiplied by ddx divided by 2. So, what will be the flux? The flux will be going out through this side will be a positive flux, and it will be f of x. It will be the value of f of x, the value of f of x. I will not consider this one because it will cancel. The value of f of x, the derivative of f of x respect to the x by ddx divided by 2, that is the value of f of x, multiplied by ddy by ddc. So this flux will be positive. What will be the flux through this other side? So the other side will be negative and will be this amount. This amount minus the partial derivative of f of x respect to the x by ddx divided by 2 by ddy and ddc. And what will be the flux through the two sides? The flux through the two sides will be entering positive, going out negative. It will be 2 times, well, minus minus is plus, so it will be the partial derivative of f sub x respect to the x multiplied by ddx, ddy, ddc. So this will be the contribution of the flux of the vector field that is going in and out from the two sides, from the two opposite sides. If I consider the other two sides and the other two sides, there are 6 sides on the cube, it will appear the partial derivative of f sub y respect to the y by ddx, ddy, ddc. And if I consider the other two sides, it will appear this expression, partial derivative of f respect to the c, ddx, ddy, ddc. Oh, and I see if I make this sum of all the terms, so I calculate the flux of the vector field over a closed surface. Surface is closed. What will be? Well, it will be the sum. It will be the flux going for all the sides. So it would be the partial of f of x respect to the x by d dx, d dy, d dc, plus the partial of f sub y respect to the y by d dx, d dy, d dc, by the partial of c respect to the c by d dx, d dy, d dc. D dx, d dy, and d dc. And what if I find the flux per unit of volume? What will be the flux per unit of volume? Oh, in the limit when d dx goes to 0, d dy goes to 0, and d dc goes to 0. What will be? Well, it will be the partial of f of x respect to the x plus the partial of f sub y respect to the y plus the partial of f sub c respect to the c. And this is the divergence. The divergence of f is the flux f scalar dds, the flux going in and out, the net flux per unit of volume. And to calculate this, we do the partial derivative of f sub x respect to the x plus the partial derivative of f sub y respect to the y plus the partial derivative of f sub c respect to the c. And now we can do the problem. So what the problem is saying? The problem is I find the divergence. So is the divergence 0? If the divergence is 0, means that the flux going in and going out is the same. One going in is negative, one going out is positive. They cancel, the net flux is 0 per unit of volume. So is the divergence 0? No. Okay, the divergence of this vector field is the partial derivative of x is 2x. The partial derivative of s sub y respect to the y, 4y. What is the divergence at the point 1, 2? Is 2 plus 4 plus 8. 4 multiplied by 2 is 10. And what is this divergence? Is 10? Is 0? No. What it means, the 10? It means the 10 means that there are the net flux over the surface is 10 per unit of volume. It means that it's going out an amount of 10 going out of the surface because is plus 10, so the flux is per unit of volume is 10 units. If the flux is negative, if the divergence is negative, is because the flux coming into the object, to the volume, is minus 10, meaning that is 10 times flux. There are 10 units of flux coming in, 10 times of net unit flux coming into the volume. And if the divergence is 0, is because the total flux going in and out is 0, so there are so much flux coming in that flux coming out through the side of the element of volumes, of elements of area that we are considering. Okay, let's go to the next problem. Next problem is straightforward, so the divergence of f is not a vector field, so I cannot put this here. It's just a number, but I can put the vector here. It's the divergence of the vector field. So it will be the partial derivative respect to the x of sine of x plus the partial derivative respect to the y of cosine of y plus the partial derivative respect to the c of the components of the vector field, the zeta component of the vector field. So the divergence will be sine cosine of x plus minus sine of y plus 2z. So the divergence is different than 0, except at the point, at what point is always, at what point will be 0. Zeta equals 0. Now I would choose, so it will not be ever 0. At the point, for example, 0, 0, 0, the divergence will be cosine of 0, 1, minus 0, plus 0, so it will be 1. So I will not find any point whose divergence is 0. So the divergence could be positive or could be negative. For example, if I choose the point x to be pi divided by 2 and the point y to be 0, the cosine of pi divided by 2 is 0. The sine of pi divided and zeta equals 0. Or at this point, the sine of pi of 0 is 0 plus 2z plus 2 pi 0. So at this point is 0, the divergence. So what it means that the divergence is 0 at this point. If you stop at this point, at the 0, 0, 0, and you imagine that you have a small sphere surrounding the points, and you calculate the flux of the vector field f scalar dds over the sphere, the f scalar dds, the total flux over the per unit of volume, when the volume v goes to 0 in the limit. When you do this, the total flux will be 0 at the point 0, 0, 0. But if you choose another point, it will not be 0. Okay, let's go to the next problem. The next problem says evaluate the line integral of x multiplied by y dds if the path is this path, r of t. Okay, let's go to do it. To do it, we have to recognize that the x of t of the curve is 4t. The y of t of the curve is 3t. So the integral that over the curve c, that in the interval t bigger than 0, less than 1, is x multiplied by y by dds. dds should be the length of the elements of the curves, the length. So it will be the integral of x 4t, y 3t. Now we need to find dds. So r of t is 4t I plus RTJ. And this is a line, it's a rectilinear line. So the object, I'm doing the line integral not over a closed curve. You can see that when t equals 1 is 4i, the vector is 4i plus 3j. When t equals 2, the vector is 8i plus 6j. So it's a rectilinear line that is described here, the r of t. Okay, so now we need to find dds. dds is related with the change in r respect to the t in magnitude. The magnitude of DDR of this is DDS. This is DDS. Because if I have r of t, I have the derivative of r respect to the t. That is a vector that is 4i plus 3j. And this vector is tangent to the trajectory. So if it's tangent to the trajectory, I may have the magnitude of ddr ddt. And the magnitude of ddr ddt will be a square root of 4 squared plus 3 squared. Will be a square root of 16 plus 9, 25. The magnitude is 5. So the DDS is the magnitude of ddr ddt by ddt. So dt is 5 times ddt. So now I can do the problem. 4t by 3t by dds by 5 times ddt. Oh, and now it's easy to do it. So the integral will be 4 by 3 is 12, t squared, 12 by 5, 16, 60, t squared. So between t equals 0 and t equals 1. So it will be 60 t cubed over 3 will be 20 t cubed, and evaluate between 0 and 1 will be 20. So the final result is 20. Let's go to the next problem. Okay, let's go to do it again. It's the same problem. So I said that DDS is the magnitude of ddr ddt by ddt. You can imagine that the vector v is the derivative of r respect to the t, and you can say that ddr is v by ddt, so the magnitude of ddr, that is dds, the magnitude of ddr, that is dds, is the magnitude of v by ddt. So it's the magnitude of the derivative of r respect to the t by ddt. This is dds. So we found who is dds. So we need to work with this integral. So who is dds? Let's go to find who is dds. Who is, first of all, who is ddr ddt? So first we find ddr ddt. Later we find the magnitude of ddr ddt. And finally we find dds. We put it here and we make the integral knowing that the x of t is sine of t, the y of t is cosine of t, the zeta of t is 2. Okay, let's go to do all the job. So ddr ddt is cosine of ti plus minus sine of tj plus 0. And the magnitude of ddr ddt is 1. Cosine squared plus sine squared is 1. So the dds is simple ddt, 1 by ddt. Okay, so what is the line integral? The line integral over the curve C when t goes from 0 to pi over 2 is the x, but the x is sine of t square plus the y. The y is cosine of t square plus the c, but the c is 2 square. Multiply everything plus dds, but dds is ddt. So now the t goes from 0 to pi divided by 2. So sine squared plus cosine squared is 1. 1 plus 4 is 5. So it's 5 times ddt. Between 0 and pi divided by 2. So it's 5t between 0 and pi divided by 2. So it's 5 times pi divided by 2. So it's 5 divided by 2 pi. And this is the result of the line integral. Let's go to the next one. Line. Okay, this problem is just a verification, but I don't see it's hard. It's just making this integral. So the first integral will be square root of 2 by t. The second integral will be square root of 2 by t squared divided by 2. If I evaluate everything between 0 and 6 pi, it will be square root of 2 by 6 pi plus square root of 2 divided by 2 by 6 pi squared. So is this the same thing that it say? Okay, let's go to do it. It will be 6 pi square root of 2 plus 6 pi multiplied by 6 pi multiplied by square root of 2 divided by 2. So the common factor here are 6 pi and square root of 2 that multiply 1 plus 6 pi, 1, and I will obtain this term, 6 pi, and I will obtain 6 pi divided by 2. And I will obtain the second term. So it will be 6 pi square root of 2 that multiply 1 plus 3 pi. And let's go to see if it's the same thing. 6 pi, 1 plus 8 is the same result. Okay. I don't know why this problem is here. Okay. So, to finalize, what we have learned? We have learned that the curve of a vector field is a new vector field. And this new vector field, let's call it C, the vector field C. This new vector field, it has a property. When you take the C, the curve of B, and you put a surface here, and you see the normal vector to this element of area. So you don't put a surface exactly, you put an element of area. And you make the projection of C over the normal vector. C scalar the vector n. When you make the components of the curve, this is the component of the curve in the direction n. Oh, what will be this? It will be the line integral of f scalar ddr, the line integral over this element per unit of area. When the area a sub I goes to 0, approach to 0. So this is the divergence that exists in this direction. If you take another direction, you need to take another element of surface and another normal. So now the C, the components of the C will be these components. So you will say that the curve of C in this direction n, nu n, will be equivalent of finding the line integral over the curve C of C scalar dds or ddl or dds or ddr per unit of area. Wow! This is the idea. And the other idea that we have found is that the divergence of a vector field f is an scalar function at any point. It measures the flux over the surface S of the vector field, the total flux on the vector field F scalar dda per unit of volume V sub I in the limit when V sub I approach to 0. And this is the divergence. And this divergence have an expression that is obtained as the sum of these terms. Okay. This is what we have done. We have done a lot. This is what we have done in this set of problems.